All right, today we're going to talk about polynomial functions and the rate of change of polynomials, continuing on with our rate of change conversations. All right, so it tells us a polynomial function is any function representation equivalent to this analytical form here, with the leading term being that a sub n x to the nth power. And then the degree would be n. So this biggest exponent is the degree of my polynomial. And then the leading coefficient is that a sub n. So we always want to put it in order. We see the exponent here is n, the next one's n minus 1, n minus 2. So we want to put it in highest exponent order. When we are looking at it that way, and our highest exponent is first, then the leading coefficient is our number right in front of the variable there. So that's going to be 3. And then our degree is that highest exponent, which is 4. If it is not in the highest exponent order, make sure that you understand the highest exponent is still the one that gives you the degree of the function. So it would be this one here. And so our leading coefficient would be 7, and this would be a third degree polynomial. All right, for our last one, I really want to rewrite that as 4x to the 0 power. Remember, anything to the 0 power is 1, and 1 times 4 is 4, and that's how we get to this point right here. And so our leading coefficient would be 4, and this would be a 0 degree polynomial. All right, so polynomials look like this, and so we want to talk about the extremum. So the extremum of a graph are the minimums and maximums of a function. There are two types of extremas. The relative, sometimes called local, so these two words are interchangeable, relative or local. And then the other type is the absolute, which is also called global. So these two are interchangeable. You can have relative or local extrema, and you can have absolute or global extremas. For relative, it tells us a polynomial has a relative minimum or relative maximum where it switches between decreasing and increasing, or at an endpoint if the polynomial has a restricted domain. All right, so for this example here, it is increasing, hits this point right here, and then starts to decrease. So this would be one of those extrema values, either a relative minimum or a relative maximum. Since it's increasing, hits this point and goes down, that would be a relative maximum. Now this starts to decrease, hits this point, and then starts to go up. So this would be a relative minimum. And then we have another one up here, a relative maximum. All right, so those local minimums or relative, remember those words are interchangeable. We've got one at -4 and we've got one at 0. So we've got two. This one right here, this is ending right there. So that's a minimum and that is a minimum. For our maximum, we've got one here and one here. And so that is going to be at -2 and 3. This arrow shows that it continues to go down. So we would not put this as one of the relative mins because that continues to go down. All right, for our next example here, again, we've got a closed point right here, and then we've got relative max, relative min, relative max there. Now, in this case, we want to talk about the absolute. And so absolute means that is the highest or lowest point on the graph. It tells us of all the local maxima, the greatest is called the absolute maximum, and the least of all is called the absolute minimum. So this point right here is the lowest point on the graph. Yep, sorry, is the local lowest point right here. But if we went through this entire function and we get to this arrow here, it keeps going down all the way. So this no longer is the minimum because this continues to go down. So this would be a local, but it would not be an absolute. So we have no absolute value. I'm sorry, absolute minimum. So we write none there. Now for the maximum, it starts right here, it goes this way, and then we just said it goes down forever. So this will have a maximum. These are our two relative maximums. And so this is the higher one, so this would be the absolute maximum as well. So we say the absolute maximum occurs at 2. That's the highest the function will be. and that occurs when x is 3. All right, so let's look at a couple more examples of that. And here we put them together, the absolutes and the relatives. And so looking at this graph, it goes down forever. So we know it has no absolute minimum. So I would write none here. Now for a relative minimum, again, it's going down on this side, it's going down on this side. This graph increases until it gets to this point right here and changes in direction and starts to decrease. So this is actually the only relative min or max. In this case, that's the top point, so that's going to be our relative max. It occurs at x equals 1. And so then there would be no relative minimum. Now, this is also an absolute max because it is the highest point on the entire graph. And so the highest point happens at 3, and that's when x is equal to 1. With a quadratic, you only get that 1. All right, here are 2 more polynomials. Go ahead and pause this and try and come up with your answers on those so that you can check them. You're looking for all of the relative mins and maxes, and then classifying if they're also an absolute. All right, so here's our answers. Notice this one does not have an absolute minimum, but again, we've got this arrow that goes down forever. So it continues without bound, so we're not going to have a minimum. We have a relative minimum at -2 right here. We've got a relative max right here. And right here. Sorry, missed that one. There we go. And then here on this second one, we do have a couple more because this decreases, then starts to increase, then starts to decrease again, and starts to increase. So we've got several relative minimums here and relative maximums. So we've got a maximum here. Oh, and I wrote that in the wrong place. Sorry, that was a relative max there, not a relative min. That -4 should have gone right there. All right, so here we've got a relative max. We've got another relative max right here and another relative max. And then we have a relative min and a relative min. And this one does have an absolute and a minimum and an absolute maximum. There's my absolute minimum and there's my absolute maximum because those are at the highest points. All right, so here's some facts about polynomials. Between 2 real zeros of a polynomial, there must be at least one local maximum or local minimum. So between 2 real zeros of a polynomial, remember the zeros of the polynomials right here when it's on the x-axis. So between these two, there has to be a local minimum, or between these two, a local maximum. That's the way the graph has to get back to the x-axis. So that's just a fact of a polynomial. And polynomials of even degree must have either a global maximum or a global minimum. So if it has an even degree, it is going to go up, up, or down, down. So something like this right here. So it has to have an absolute max or min, or a global max or min. The next characteristic of a polynomial we're going to look at is the points of inflection. A point of inflection occurs when a function changes from concave up to concave down, or concave down to concave up. At a point of inflection, the rate of change of a function changes from increasing to decreasing, or from decreasing to increasing. And so looking at our graph here, it says the graph of g of x is shown in the figure above. Use the graph of g to answer the following. Find any values of x where g has a point of inflection. So we see that it is concave up right here, and then concave down, and then concave up again. So we have changed in concavity there, so we do have a point of inflection. We would have a point of inflection about right there, and you can't say approximately on these. This is concave up, this would be concave down. So a point of inflection at -1 It is now concave down until it gets to right about this point, then it switches concavity again. And so we have one at x equals 1 as well. So the point of inflection is where it changes concavity. All right, for each of the following intervals, determine if the rate of change of g is increasing or decreasing. Explain your reasoning for each answer using features of the graph of g of x. So we're talking about this graph up here. And so it wants to know on the following intervals if the rate of change is increasing or decreasing. And so we talked about concavity tells us if the rate of change is increasing or decreasing. So when we look at 3 to 4, 3 to 4 is right up here. And so in this case, we are on the concave up. So we can say the rate of change is increasing because g of x is concave up. You can also tell that the rate of change is increasing because it does get steeper here from 3 to 4 than it was previously. So here it went up 1 over 1 basically, and here it went up about 3 over 1. So our slope would be 3 on this one, and our slope here would be 1. So you know it's increasing that way as well. But when it is on the concave upside, we know it's increasing, so we can say that. For the next interval from -4 to -3, -4 to -3. So we're looking at this portion of the graph. Again, it's on the concave up, so our rate of change would be increasing. I'm going to go ahead and use the abbreviation for that. ROC for rate of change is increasing because the graph is concave up. All right, for -1 to 1, so now we're looking from here to here on our graph. That's this part right here, so that is concave down. And so in that case, we know that the rate of change is decreasing. So we would say rate of change is decreasing because g of x is concave down there. So that's what we're doing with the concavity and the rate of change. All right, the last question that we're going to look at here is a calculator question. And this is to make sure that you can use the calculator to find the different attributes of those polynomials. It says for 0 to 3 on t, the number of cars in a parking lot at time t hours can be modeled by this function. So I go to my y equals, and I'm going to put in my equation. Oops. Be careful to make sure you get the correct equation in there. All right, now that we have our equation in the calculator, I'm going to go ahead and hit graph. Now I can tell that this graph here, I'm not seeing the whole thing. I see this portion of it, and then it goes up into the top and it comes back down. So I know that I'm going to have some kind of max there. So I really do want to see that on my window. And so I'm going to look at the table because it said on the interval from 0 to 3. So let's look at what those numbers are. Right there, I see that's 26.505. That is not necessarily the highest point, but at 2, it's that high. So I know I need my window to go at least that high. So I'm going to go to window here. Get this right on the screen correctly. There we go. And I'm going to make sure that my Y max is above that 26 so I can see it. And it doesn't have to be just right above. I'll go ahead and go to 50 just to make sure that I can see it. And so there is a better view of our graph. All right, so it says, based on this model, at what time t does the number of cars in the parking lot change from increasing to decreasing. And so on our calculator here, we could see all of this is increasing until it gets to this point and starts to go back down. So the point that it's asking for is that relative maximum or local max. Remember, those are interchangeable. So we want to find that value right there. To do that on the calculator, you hit second trace and go over to maximum. And the calculator is asking you left bound, so you want to go somewhere on the left-hand side of the graph. And so I'm on the left right there, so I can go ahead and hit enter. Then it asks me for the right bound, so I want to go to the right side of the graph. Anywhere on the right side is fine. Then we hit enter, and then you want the calculator to guess. That's what it's asking. Do you want me to guess? Yeah, the calculator's a great guesser. So I hit enter, and there it is. The maximum is at 2.46, so I'm going to write this point down, 2.4. 61 and 33.832. So this is that vertex relative maximum point right there. All right, I apologize for that. I wrote down the wrong number. So there it is, 2.446 and 31.898. So that is our relative maximum or our local maximum. And so the question said, at what time does that happen? And so we know that the time is being measured by this x value. And then our c value is measuring the number of cars. So you do have to interpret that answer that you just found there. So I would say at 2.446, the number of cars in the parking lot changes from increasing to decreasing. So there's an example from a context problem and using the calculator on how to find those relative max or mins. You should be able to get that relative max or min from a calculator in either, if you're given an equation, and then you should be able to get it from a graph if you're given a graph. That's that multiple representation for you to be able to get the different attributes. On the last part of your notes there, we had that quick explore for polynomials, similar to the one we did with linear and quadratics last class. And so here it is. I've gone ahead and filled it out just so that we can discuss a couple things. With the linear equations, we said our first differences or our rate of change was constant. With the quadratic, our second differences or the rate of change of your rate of changes was constant. Here's a cubic. So this third difference is what's going to tell me what it is. So this was, if these were constant, that would be linear. If these were constant, that would be quadratic. And so our third differences there are constant. So this is a cubic. That's going to be true for all polynomials. If it went out to fourth difference, then it would be to the fourth power. If it went out to the fifth, it would be to the fifth power. All right, some more stuff here on the rates of change. It asks us, is the rate of change of S increasing or decreasing over the interval 3 to 9? And so we would want to use these values right here from 3 to 9. So we would take that 157.10 minus the 250.70 and then divide it. And so it is decreasing. We can also see that from the graph here if we went from 3 to 9. And so our 3 is right here and our 9. And so our secant line, this line right here, is a negative slope line, so it is also decreasing from that way. So you can see it by seeing the negative slope from the table or the graph. There's that multiple representation. And then at the end, you had another example of those tables. And so we worked this table, first differences, second differences, third differences, and the fourth differences are finally the same. And so that's a fourth degree polynomial. And you can only check those differences like that without checking the average rate of change if you've got an even interval, which this is by twos. If they're equal length intervals is better said. All right, there's our polynomial attributes.